This video is the Schrodinger equation part 2, so if you haven't seen it, you might want to watch part 1 here first. On the other hand, if you're just here for me to explain the derivation of the equation and how to use it, stick around. Okay, so if it was your task to build a new theory of physics, you'd need to decide what things are so fundamental that you should build them into the theory. Conservation of energy is probably high up there on your list, as it clearly was on Schrodinger's, because that principle is baked right into quantum mechanics via the Schrodinger equation. Suppose we have a particle with this wave function at the start. Remember, we can write our state in any basis we want, so a perfectly valid one is the energy eigenbasis. This means we can always write a state as a superposition of different energies. And remember, if we measure the energy of that particle, it'll just be one of those with this probability. Now, say this state evolves in time. In other words, we apply the time evolution U. What condition do we want to impose on the new energies of the state? In other words, how do we want conservation of energy to look like in quantum mechanics? First, let's look at the special case where a particle just has one energy E when we start. In other words, it is an energy eigenstate. Then we evolve it forward in time and look at the energy of the new state. Now, we definitely want that to be E, because otherwise energy is definitely not conserved. So that's the first thing we'll require. But we'll require more. Going back to the general case, if we looked at the average energy of the particle, that also shouldn't change after some time. Because if, on average, the energy has increased, I don't think we'd be willing to say that the energy of this particle was conserved either. In fact, let's ask for even more from conservation. If we were to measure the particle's energy initially, you have this probability of measuring this energy. Well, let's require that if instead you measured it afterwards, you have the same probability of getting that energy. You can't tell the difference between the two states by measuring energy. This requirement is pretty much strong enough to give us the Schrodinger equation, as we'll see. We can always write the final state as a superposition of energies, just because we can do that with any state. But we can't have another energy in here that wasn't in the original. That would mean that there was a 0 chance of measuring that energy originally, but later that chance was not 0. We just need to know about how the coefficients have changed in the new one. We want the probabilities to be the same, but that probability is just the length of this complex number squared. So this number here better have the same length. Let me draw this complex number as an arrow for a second. Then this complex number here is the same length, but it might be rotated. Let's call this angle of rotation theta. There's a convenient way to represent rotations that we've seen before. This equation says that the new coefficient is the old one rotated by an angle theta. Okay, so let's put all of these in for all of the energies. Great, now we're almost done. 2 little things though. First, these can't all have been rotated by the same amount. Why? Because then this rotation can be brought out to the front, and now both the future and present state are essentially the same. That's because this overall rotation here doesn't affect any measurement outcomes. But that would mean that no matter what crazy situation you put the particle in, it does nothing. So that's not right. So the only solution is to make sure that these angles here are different for every energy. Also, the amount of rotation should depend on how much you've gone forward in time, so that if you've only gone forward a little bit, you've only rotated a little bit. That suggests that the right amount of angle to rotate by is energy times time. Oh, and throw in some constant there to deal with units and scaling and all that. And we're done. That's what the Schrodinger equation tells you will happen to the state. But let's talk a little bit about using it now. Say that we start with this state where this energy is twice as big as the lowest energy and the next is 3 times as big, and these are their coefficients. As you evolve it in time, the second one's angle changes twice as fast, and the third one 3 times as fast. But regardless, you might be thinking that these states hardly look different, and that's kind of right in this basis. But if you look in another basis, the difference can be much more obvious. For example, Suppose that in the position basis, each of these had wave functions that looked like this. Then at the very start, when you add them up, the probability of finding the particle at various points looks like this. But see how that evolves in time to give a probability distribution that changes dramatically. The reason is these complex numbers. At the start, they all just add like normal to give you this. But later in time, when these complex numbers are pointing in different directions, they don't just add up anymore. As an extreme example, if these two arrows pointed in opposite directions, this would mean that they subtract from one another. This is why the overall wave function in the position basis can vary so much over time, so that, depending on the time you measure, the particle might have a very big probability of ending up here versus here instead. Yet, if you measure energy, you always get one of these three energies with these probabilities, no matter what time it is. This is in general true. Things look pretty calm and unchanging for measurements of energy, but they can look very, very different when measuring something else. And that's it, everything that you need to know about the Schrodinger equation. Okay, just kidding. There's one last bit to it, and yeah, it's kind of a big deal. How do we know what the energy eigenbasis is? If we take an energy eigenvector, how do we find out what it looks like in the position basis? Well, thankfully, Schrodinger also gave us an equation that defines what an energy eigenstate is, and it's what you'd expect as well. The issue is, this equation is spectacularly hard to solve. By that I mean it's probably impossible to solve it mathematically for just about anything bigger than two particles. You just have to resort to doing it by computer, preferably the supertype. That's why physical chemists do so much hard work on the Schrodinger equation, and it's something that I feel completely underqualified to talk about, since as physicists we tend to put these problems into the too hard basket. Maybe if I do learn it one day, we can come back to it. But let's for now move along to homework time. First, throughout these two videos, I kept talking about predicting the future and that if you know the present state, you can predict the future state. Does this mean that quantum mechanics is deterministic? If you don't think so, comment on where the determinism ends and the randomness starts in this theory. Second, show that for the Schrodinger equation, this is true, that it's the same thing to go forward in time t1 plus t2 as to go forward in time t1 and then go forward in time t2. This seems obvious, but explain what the philosophical consequences of this might be. Third, I said that linearity follows from the Schrodinger equation. Can you see why? Try and prove it. Please type your answer in the comments, but afterwards you can click this link for a video of a short proof of it. Yours will likely be a little bit different though, so I think it's really interesting and helpful if you write down your answers first. And fourth, this is for people who've done quantum mechanics before and know that in this theory, time evolution is unitary. Yet I just went on about linearity so much in the previous video. Show that linearity plus the assumption that time evolution maps valid states to other valid states is equivalent to saying that evolution is unitary. I'll put the proof of that in the video there as well. So sorry these videos and my replying to comments has been so haphazard lately. As you might know, I started my PhD recently and I'm finally settling into it, so hopefully I'll be a little bit more consistent from now. But more about that soon.